Hi, in this lecture, we will build a machine learning model which will help us predict the spread of viruses like COVID with the help of the epidemiological model plus machine learning. So this is coming under the category of scientific machine learning, which is a fast emerging field which allows you to get the best of both worlds, which is the world of machine learning and the world of science or phenomenological models. So in this lecture, let us try to understand how this can be done for a very simple problem statement. So firstly, let us look at the science of how a virus spreads. So this applies universally for pretty much all types of virus. So there are many different models that people have developed. Some of them are very complex and some of them are the early versions of the theoretical models, which are very simple. So today, to model the spread of a virus, we'll be picking a very simple model called as SIR model. This model compartmentalizes a given population of people into three categories: susceptible people, infected people, and recovered. Susceptible people are whoever can potentially catch a virus. So initially at the starting, everyone is susceptible. If there is one person who has, let's say, COVID, then all other people in the population they can potentially get the virus in the future. So they are all susceptible. Infected is the number of infected people at any given point of time, and recovered is the people who go from the infected category to the recovered category. So here we are ignoring a lot of things like the number of deaths we are ignoring. We are keeping the model very simple. Now, we can model the change of number of susceptible people, number of infected people, and number of recovered people such that we can get it as a function of time, starting with certain initial conditions. So initially, the entire population is susceptible. Then the susceptible people will move from being susceptible to being infected. So that's why this is called as a three-compartment model. Initially, you consider that the susceptible people are in one compartment. Then they move to the compartment of infected people, and then the infected people move to the recovered compartment. The change of these three variables, S, I, and R, can be modeled using three ordinary differential equations. So ds by dt signifies the rate of change of S, and S is susceptible. di by dt is the rate of change of infected, and dr by dt is that of recovered. So just notice a few things. Susceptible population can only decrease with time because initially nearly 100% of the population are susceptible. But as more and more people get the virus and as more and more people recover, the number of susceptible population decreases. And here it's also assumed that once you recover, you don't get the virus again because you get the immunity. But that's also a simplified version of the model. In reality, we know that things are different. But let's keep it very simple for today's purpose. So ds by dt, which is rate of change of susceptible, is having a negative sign, first of all, to signify that the number of susceptible people are decreasing with time. So that's why ds by dt is negative. Now, there are three terms here. One is this tau si, then there is s and I. S is the susceptible population, I is the infected population. So basically what this equation is saying is rate of change of number of susceptible people at any given point of time is proportional to the number of susceptible people. It's proportional to also the number of infected people, because if there are more infected people, they can interact with the remaining susceptible population. If there are more susceptible people, they all can get potentially infected. So both S and I affects the rate of change of S, ds by dt basically. And there is an interaction parameter. So tau si is a parameter which needs to be experimentally estimated, or somehow using epidemiological models, you have to come up with a value that is valid for tau si. And the value of tau should be positive, but you have a negative sign attached here. So overall, this quantity will be negative. di by dt, you might notice that interestingly in the di by dt, there is a positive term, which is exactly this term. So this term tau si multiplied by si is also appearing here, but with a positive sign. That is because the people who are susceptible will move, once they get the virus, they will move from the susceptible to infected category. So this rate of change, whatever is happening there, where are they going? They are directly going into the infected category. So that is why you have a plus sign here, because when susceptible people move from susceptible to infected, that increases the number of infected people. So there is a plus sign associated with this. But there is one more term here, which is tau IR multiplied by I. So I is the number of infected people So the more there are the number of infected people, the more the number of people who are also recovering, right? Because if there are 1,000 people who are infected, maybe, and the recovery rate is some one person recovers in every week, then there is 1,000 people means all the 1,000 people can recover by the end of the first week. So the more there are infected people, the more the rate of decrease of infected people, or vice versa, more the rate of increase of recovered people. So tau IR is a term which signifies the interaction term between infection and recovery. But please note that here there is no physical interaction between infected people and recovered people. There is nothing like that. That's why you have only the infected I term here. There is no R term. But there is a negative sign because as the people move from infected to recovered category, di by dt has to be has to have a negative contribution towards di by dt, because when people move from infected to recovered, it's causing the infected number to decrease. So that's why here there is a negative sign. Now, where are these infected to recovered people going? They are directly going into the recovered category. And where is that? So dr by dt, you will find there is this exact term tau IR times I, and with a positive sign, because the number of recovered people will only increase with time, because initially nobody has recovered, and slowly the number of recovered people increases. And ideally, if the entire population gets the virus and they recover, initially the entire population is a susceptible population, then slowly they move into infected category, then at the end of it they all move into the recovered category. Here obviously we are assuming that there are no deaths happening. So this famous model is called as the SIR model. It's the basic versions of these models are 100 plus years old. There are many other sophisticated models also, like SIR, then hospitalized and dead. So two more compartments are introduced along with SIR. There is also a model called QSIR. So QSIR model was famously introduced by Dr. Raj Dandekar from our team, who finished his PhD from MIT. So this work introduced a quarantine factor to account for the fact that during COVID, artificially quarantine is introduced by humans, like by government policies. And this quarantine factor can be captured using a Q factor. So the original SIR model was modified to introduce QSIR model. So it was a 4-compartment model, but there is also the Q is not easy to scientifically model. So that was a novelty of the work, which was later published in Cell Patterns and other journals. I will share the link to the paper in the description. And this is a small GIF showing a simulation of how the virus spread affects a population. So I hope this can be played. Yeah. So now you will see once the GIF starts playing. Yeah, so what do you see now is initially there was only one infected person, and slowly, so these red people are all infected people, black are all susceptible people, and slowly you can see that all the susceptible people are getting infected, and then green are recovered people. So slowly then the red people who were infected will move into the recovered category. So it starts from a few infected people in the population moving to most of them becoming susceptible to infected, and then finally all of them recovering. So the problem with this model, although it's very simple and easy to solve, the problem is that these interaction parameters are unknown in real life. We have no idea what is this tau SI or tau IR. So tau SI is the interaction parameter between susceptible and infected. Tau IR is the interaction parameter for people going from infected to recovered. And the problem is different viruses have different ways of spreading, different rates of spreading, different incubation period. A lot of parameters affect the rate of, let's say, virus spread or the virulity. So these parameters are pretty much very difficult to identify in real life, which is why the SIR model is not that great to directly use to model virus spread like COVID or any other pandemic. So what can we do here? One good solution that we can think of is incorporating machine learning so that we can make better predictions. And what predictions are we talking about here? Predictions could be about how does the susceptible, infected, and recovered people, that population change with a function of time. So ideally, we want less number of people to get infected. That's what our goal is, right? If we were a part of the government making the policy, we want lesser and lesser population to get infected, ideally, so that lesser and lesser people will die. So we want to make predictions of S of t, I of t, and R of t, which is susceptible, infected, and recovered as a function of time. So what does a traditional machine learning model do? A traditional machine learning model can be thought of as something like this: a neural network with multiple hidden layers. And you could potentially think of it like having three inputs: the initial susceptible population, initial infected population, and initial recovered population. And with those as the inputs, let's say you are trying to predict the number of susceptible, infected, or recovered people, let's say at the end of the month, something like that, so that you can know where the virus is heading. Now, to make predictions like this, you will have to train the neural network with large number of data sets of virus spreading at different places. Maybe let's say you have 50,000 small and big cities all over the world. And if you have the data of the initial population distribution versus final population distribution after the end of a month, then maybe you can use that data, which is available on various websites on internet, to train a neural network so that for a new population who's susceptible, infected, and recovered, that setting is known, we can try to predict the change in these three numbers at the end of 1 month, let's say. A very simple traditional machine learning model. This is possible to do. But the problem here is we have no idea what's happening inside this ML model, which is also why a traditional machine learning model is called as a black box. Black box because it makes predictions, but we have no idea what's happening inside. There is also one more problem. So the problem is this. In real life, if you look at the SIR model, this tau SI and tau IR, these parameters are unknown. Agreed. However, we still know these relationships are valid because the rate of change of susceptible population should be inversely proportional to the number of susceptible people and also number of infected people. Because the more there are susceptible people, more of them can get infected, which means ds by dt should have a negative correlation with S as well as with I. So the fact that S and I are involved in the ds by dt with a negative sign, that relationship is known. Similarly, for di by dt, we know that S and I should be involved with a positive sign. Similarly, the infected I itself should be involved separately with a negative sign because the infected people themselves recover. So there is a rate of recovery. Same for the recovered dr by dt, rate of change of R, which is dr by dt, should also be proportional to I. So all of these things we know. So there are certain things which are known in the SIR model, even if these tau parameters are unknown. So why should we throw all of this knowledge into the basket, right? Why should we not consider the fact that this relationship is known, this is known, this sign is known? So there is a lot of knowledge in this equation or in this system of three ordinary differential equations, even though in real life some parameters may be unknown. So this is where the power of scientific machine learning comes into the picture. In scientific machine learning, instead of using black box models like this, what we do is the following. We retain the ordinary differential equation where some terms are known, but whichever terms are unknown, we can replace with a neural network. So here, the tau SI, which is the interaction parameter between susceptible and infected, they are unknown. Similarly, tau IR, that is also unknown. So what we can do is we can replace those unknown terms with a neural network. So when I was learning about scientific machine learning in the very beginning of my journey, I had a doubt like, what does this replacing with neural network exactly mean? What it simply means is you replaced, so tau SI should take some value, right? 0.85, whatever, 0.2. It is a number at the end of the day. So instead of treating it as an unknown, or instead of entirely replacing this whole system with a neural network, just that unknown number you treat as the result of a neural network's prediction. So whatever this neural network is predicting as a number, you use that number as the proxy for tau SI or tau IR. So you have to use different neural networks because tau SI and tau IR are two different interaction parameters. So you of course need two different neural networks here. So, but you see the power of this kind of a model. The power is that you are not throwing away the equations entirely. You are only replacing the unknown terms with the neural network. So this combination of differential equation plus neural network is called as universal differential equations, where it's called universal because you are approximating unknown terms with a universal function approximator. So neural networks are called as universal function approximators. And this is not neither an ordinary differential equation nor a fully neural network based system. This is ordinary differential equation plus neural network. So that is why it's called universal differential equations. So here, basically, we leverage the science of epidemiology, like SIR model. It could be more complex models also. So basically, we use that science of science that we know, but we combine the power of predictive power of ML so that we have something better than a black box model. So it's not a fully black box model. It's also not a overly simplistic model like SIR, but it has the best of both, right? So this is called universal differential equations. Now, a UDE for SIR model, susceptible, infected, recovered model, can look like this. So here, ds by dt, instead of it being minus tau, this should be Si. Instead of minus tau Si, you replace it with neural network. So you need two neural networks because this tau Si is appearing here and here, whereas here it is tau IR, right? So tau IR terms which are appearing in two of these equations, you replace with NN2, which is the proxy for second neural network. Tau Si is replaced by NN1, which is the proxy for the first neural network. Now here is my question. What are the inputs to these neural networks and what are the outputs? So let us think about that, right? So this mental exercise that we are going to do right now will give you a fairly good idea about what exactly is this UDE, universal differential equation. How can it make predictions in a more scientific way? So this is what we are doing. The neural network 1 has two inputs. So let's say we are starting at time t equal to 0. So we know the initial susceptible population and initial infected population. So let's say this neural network is undergoing training, or it's after training, it could be either. So you pass the initial susceptible and infected population, and then based on this input, the neural network will try to make a prediction. And this prediction, we are saying that it is supposed to predict the tau Si. Now what we do is this tau Si, this neural network 1 is predicting this value, we will plug in here, right? So here, this is tau Si, this is also tau Si. Similarly, the neural network 2 gets the infected population as the input, and given I of 0, it is supposed to predict the the tau IR term, the infected recovery interaction term. So this is the neural network 2. And where does this go? Tau IR that is predicted by the neural network 2 is used here and here in this system of ordinary differential equations. So this is the SIR model only, but except now what you have is you have a predicted ds by dt, you have a predicted di by dt, and you have a predicted dr by dt. These are not the actual ds by dt, di by dt, dr by dt. These are predicted ones. Predicted by whom? Predicted by the neural network in the UDE. Now, what you can do is you can solve for s of, let's say, 0 plus delta t for a new time point. Similarly, I of 0 plus delta t. So you can solve for from the knowledge of s of 0. So you know the initial conditions, you know s of 0, recovered of 0, or infected of 0. From this and from the knowledge of ds by dt, which is predicted using the neural network, you can now calculate or estimate SIR for a new time point, let's say 0 plus delta t. And how do you do that? You do that using numerical integration. So numerical integration can be done in very sophisticated manner. Here I'm showing you the simplest, like a Euler method of numerical integration. So here predicted value of S, predicted value of I, and predicted value of R at time point 0 plus delta t is equal to S of 0 plus predicted ds by dt times delta t. Similarly, predicted value of I at new time point equal to the actual value of I at the initial time point plus di by dt, which is predicted, times delta t. And similarly, same thing applies for recovered population. So this is the numerical integration that we are doing to calculate the susceptible, infected, and recovered predicted values after we use neural network for predicting the ds by dt, di by dt, and dr by dt. Then now, how do we know that if these predictions are good or not? Like These are predicted values of Si and R at a new time point, right? So we don't know how good these predictions are. So to train the neural network, we have to compare these numbers with a ground truth and then modify the weights of the neural network based on how far away these predictions S cap, I cap, and R cap are from the actual values. So now actual values are what? Actual values are if you assume that you know the tau Si and tau Ir. So let's say this is 0.85 and this is let's say 0.1. Let's say you knew the interaction parameters tau Si and tau Ir for a particular virus. Then what you can do is you can plug in that here and numerically solve the system of differential equations. So basically here, instead of using the predicted ds by dt, predicted di by dt, and predicted dr by dt, you use the actual ds by dt, actual di by dt, and actual dr by dt. How? By plugging in, let's say, the known values of interaction parameters into the SIR model over here, and then use that to numerically solve for S, I, and R for various time points. So it won't be just for t, 0 plus delta t, it will be for various time steps. So you can basically have an array of predicted value of S at time point, any given time point ti, predicted value of I at given time point, and predicted value of R at any time point. Similarly, you can have ground truth S for time points, ground truth value of I, and ground truth value of R. Now, to know how good your neural network was in predicting your di by dt, dr by dt, and ds by dt, all you need to do is compare these terms. If these terms are very close to each other, then your neural network was making good predictions. Otherwise, it was not making good predictions. So this enters in the loss function. So here the loss term that we are defining, which is a measure of how bad your neural network predictions are, we use something called as mean squared error. One way to define the mean squared error here is if you have n time points starting from I equal to 1 to n, you do 1 by n times sigma I equal to n, 1 to n, s cap minus s at time point ti, the whole square. So you are taking, this is error, right? This difference term is an error. This difference term is an error. Predicted minus actual value. I mean, actual minus predicted value. This difference term is also an error. So error you are squaring because you want error to stay as a positive number. And then you are taking the mean of that. You are summing it up and dividing by n. So that is why it is mean of square of error, MSE. You use this as the parameter which you want to optimize in your neural network. So you will modify the weights of the neural network. So let's say you define the weights of NN1 as theta1 and NN2 as theta2. Then you modify the weights such that NN1 of theta1 will give you some outputs, right? So theta1 new equal to theta1 old, the previous value of theta1 minus some learning rate times dou mean squared error by dou theta1. Similarly, theta2 new equal to the new value of theta2 equal to theta2 old minus some learning rate times dou mean squared error by dou theta2. So by continuously doing this, you can modify the parameters of your neural network, the weights and biases, such that this neural network will be able to make better predictions later once the weights and biases and those parameters are optimized. So with that, we are ready to construct our UDE, Universal Differential Equation. So before we write the code, let us think about the steps that we are going to do, right? So we should first define the initial conditions. Initial conditions are S of 0, I of 0, R of 0. 0 means at time point t equal to 0. We also need to know the, if we want to generate the ground truth, we should know the interaction parameter. But of course, tau Si and tau Ir, we will not be using in training the neural network, because obviously what we are training the neural network for is to predict this in the first place, right? So this will be used only for ground truth. So we can define the constants that we will use in our construction of UDE as well as the initial conditions. Then solve the ODE. What is the ODE? The ds by dt, dr by dt, di by dt, and dr by dt. So these three ODEs we can solve numerically using fourth order Runge-Kutta method or using Euler integration. Any method, it does not matter, to generate the ground truth data. So ground truth data would be nothing but a plot which would look like this is, let me draw this once again. So this is time, and this is maybe the number. So initially, everybody is in the susceptible category. So initial population, let's say this is 1. 1 means fraction of population. Everyone is susceptible. And then later they become infected and then go to recovered. And infected population will increase in the beginning. It reaches a peak and then they recover. Then they come back to 0. Similarly, recovered population will increase, and everyone will at the end of it recover. So this is S of t, this is I of t, and this is R of t. So we should have a plot like this, and this will serve as the ground truth data against which we will compare the predictions made by the UDE. So now, once we have the ground truth data, we are ready to define the UDE. So in defining the UDE, basically what we are doing is we are defining the neural network NN1 and NN2 that we mentioned here. And we will be training the neural network such that neural network is able to make good predictions on the tau SI and tau IR, such that once we numerically solve for the SI and R using this framework, which we mentioned here, the UDE framework, it should match very closely with the ground truth S, ground truth I, and ground truth R. That's our goal. So we define the UDE, we train the neural network, and then we solve the UDE. We solve meaning we make predictions using the tau SI and tau IR parameters which the neural network predicts. And then we can compare and see how good the ground truth data SIR and and the predicted SIR values are using plots. Then one last thing which we can do is extrapolating. So extrapolating meaning we'll be training from, let's say, time t equal to 0 to, let's say, t equal to 25 days or something like that. So then now the UDE framework will be only trained for 25 days worth of data. Now what we can see is, okay, from this training and with the parameters predicted by the UDE, the tau parameters predicted by the UDE, can we make predictions from, let's say, day 26 till day 50? Is this possible? We will see that. So this is what we are going to do in the rest of this lecture, where we will be defining the code and running it in Julia, because Julia has very good frameworks for implementing universal differential equation framework. So we'll now be opening Julia and we'll be running the code. But just before that, I'll give you a walkthrough through the code block by block, explaining every single line of the code so that you know what we are doing. So the first thing that we do is we import the required packages in Julia. So I'll be running Julia in Jupyter Lab in Jupyter Notebook. So I'll be using differentialequations.jl, random.jl, Lux for the neural network, and then plots.jl for plotting, and a few more packages which you will see where we are using. Then in this block of code below, we are defining the constants and the initial condition. So initially we'll start with simulating for 25 days, and total population we are normalizing to 1 so that we can later multiply by any number and get the total population, whether it's 300,000 or 5 million, whatever. Then the initial conditions are what fraction of the population are susceptible and what fraction is infected and what is recovered. So initially we will set recovered to be 0 because nobody has recovered in the beginning. And we will say 1% of this population is infected. So that is S0 multiplied by 0.01, which means the total population, if it is 100, 1% has infection. 1 person has infection. And 99% of the people are in the susceptible category. So they are the initial conditions. Then here in this P0 parameter, we are defining the ground truth values of the tau SI, the infected to recovered interaction parameter. Susceptible to infected interaction parameter and infected to recovered interaction parameter. So tau SI is 0.85 and tau IR is 0.1. And we are defining the time span to be from 0.0 to 25.0. That is this. And we are creating a time variable, which is a set of numbers ranging from 0 to 25. So this part is that fairly easy. Now what we do is we generate the ground truth data by solving the SIR model. So we define this SIR function where the parameter U has all the three variables S, I, and R. Similarly, the parameter P has tau Si and tau Ir ground truth values. And we use absolute value to ensure that these parameters are non-negative. So we want tau Si and tau Ir to be positive numbers because that is the rationale for using the negative signs here. Now, du1, du2, and du3 are the first derivatives of the three parameters of u. So u of 1 is S, u of 2 is I, and u of 3 is R. Similarly, du of 1 is the equation for ds by dt. Du of 2 is the equation for di by dt. And du3 is the equation for dr by dt. So minus tau Si times Si, that is the du1. Then tau Si, so this term is same as this term except with a negative sign. And then, so this is the rate at which people are going from infected to susceptible to infected. And this is the rate at which people are recovering, which is why it's having a negative sign. And all these recovered people are directly going into the recovered category. So that is the function called SIR function. And then we define the problem that we want to solve using this function called ODE problem. So this is from the package that we imported. It's already predefined. We don't have to define this ODE problem function, to which we pass the problem statement, which includes the ordinary differential equations. So SIR is this function. We pass the initial condition U0. We pass the time span for which we are solving. And we also pass the parameters, the tau values, which are the ground truth parameters P. So now, if you look at it, the du is the quantity that we are basically solving. U0 is the initial condition. Time span is here and P0 is here. So I think I might have flipped the order of time span and P0, but we'll see. Then true solution is nothing but we solve this problem statement using a solver. So this TSIT5, it is basically a fifth order Runge-Kutta solver, and it's proposed by this person called Sitora. So TSIT is basically the first four letters of his name. And using that solver, we'll also be saving the solution at all the time steps that we are solving. So save at equal to T will make sure that we are solving the solution periodically. And then the true solution, which is the ground truth, we are saving here. And in this, there will be two things, the timestamps as well as the solution for the parameter Si and R. Now, we are constructing, and here, basically it will be in U, right? So U of 1, U of 2, and U of 3 will give us SIR. Then we are constructing the universal differential equation. So first, we use a random number generator so that we can initialize the neural network using random initial parameters. Then we have to define two neural networks, right? So first one is neural network for predicting the tau Si term and neural network for predicting the tau Ir term. And we are using this lux.chain function. So this lux, if you remember, we imported the module called lux in the beginning. So lux.chain will allow us to construct neural networks sequentially, very similar to how we do it in Keras in Python. So here we are defining a dense layer fully connected with a rectified linear unit activation function. So the first neural network, NN1, if you remember, it had two inputs, S and I, which is why the input layer has 2 as the dimension, hidden layer has 10 as the dimension, and output layer is a fully connected layer with 1 output. So the neural network is like 2 here, 10 here, and 1 here. So this is the architecture of NN1. Similarly, the architecture of NN2, which is the neural network for predicting IR, will have only 1. Instead of 2 nodes here in the input, it will have only 1 node, 10 in the hidden layer, and 1 in the output layer. So that is for predicting tau IR. Then these are the states and parameters of the first neural network. And here is where we pass the random number generator. So in the lux.setup, we pass the random number generator plus the neural network architecture, which we defined just above. And then we get the initial neural network parameters. Now, by using this initial neural network parameters, we can, first of all, we want to store all of these parameters in a structured array format. So this P0 vector is basically that component array which we can use for neural network training. So we want to optimize the neural network parameters during the stochastic, using the gradient descent, whichever gradient descent that we are using. So it will be converting this P1 into P0 vector format. Here, for a moment, ignore this soft plus function. I'll come to explain what exactly is that, why we are using it. Basically, now the UDE is here. If you look at the UDE function, it's very similar to the SIR function which we defined above. It has DU, U, P, and T. So SIR is stored in the variable U. So U of 1 is S, U of 2 is I, U of 3 is R. And the neural network here, NNSI, is the predicted value from the neural network 1. And what is the predicted value? It is the prediction for tau Si. It's nothing but we are calling the neural network with S and I as the inputs, current value of S and I as the inputs, the layers in the parameter P, and then the state variable st1. If you look at the state variable, it was defined here. And then neural network 2, which is supposed to predict tau IR, it is NNIR, and NNIR is defined here, NNSI is defined here. And to that, we are passing the current value of infected variable. Then P dot layer 2 should ideally store the store this guy, basically the weights and bias parameters of the neural network 2, and then state variable 2. And then we will predict tau Si and tau IR. It's nothing but the predictions of NNSI, the predictions of neural networks themselves. But then you might be wondering, so what is this clamp and soft plus? So first I'll explain clamp. Clamp is nothing but something that restricts the value of tau Si between a very small number, very small positive number, and 1. Because the interaction parameters, if you remember, their ground truth values are 0.85 and 0.1. So this tau parameter is always between 0 and 1. We don't want it to be negative. We don't want it to be greater than 1. So this clamping function will allow your tau Si to be between these two numbers. Now then, what is this soft plus? So if you look at the definition of soft plus here, it is logarithm of 1 plus exponent of x. So log of 1 plus exponent of x is approximately like ReLU of x, which is max of 0, x. So basically, if you do log of 1 plus exponent of x, you are essentially getting a differentiable version of rectified linear unit. And you know what rectified linear unit does? It basically converts your inputs into positive. If positive number is the input, it will be retained. If you have negative number as the input, it will be converted to 0. So this log of 1 plus exponent of x is approximately doing this, but in a more differentiable way. So what this does is it makes sure that this inputs NNSI into the soft plus function. If they are negative, this soft plus will convert that into a number which is very close to 0 or very close to max of 0 and that number itself. Now, what we can do is now we can calculate the predicted value of ds by dt, predicted value of di by dt, and predicted dr by dt. So predicted ds by dt is du of 1, and that is minus tau Si times Si. Now, this tau Si is not the ground truth tau Si. It is this tau Si which you get from the neural network's output. Similarly, this tau IR is not the ground truth. It is what you get from this NNIR after ensuring that it is between a small positive number and 1. So now you have predicted ds by dt, dr by dt, di by dt and dr by dt in these three numbers. Here, actually, you have like an underscore. It's basically to ignore the second value that is returned by this function. It's like a state variable, which you don't want. You just want the neural network output. Now, the function, this is the end of the function. And then you define the UDE problem which you are going to solve. UDE problem that you are going to solve is defined using the same function which you used earlier. The function that we used earlier for defining the SIR model for ground truth was the same function ODE problem, to which this time we pass the SIR UDE function. We pass the initial condition U0. We pass the time span 0 to 25 days. And then the P0 vector. P0 vector is the parameters of the neural network, which we had here. P0 vector, the first layer was P1, second layer was P2, P1 and P2 were the randomized parameters of the first neural network and second neural network, respectively. So till here, nothing will happen. Neural network will still, we are still defining, we are not still training the neural network. So now we can define this loss function, which is the mean squared error loss function. So for the loss function, first of all, we need a solution for the UDE, meaning the UDE should predict a SIR value. We already have the predicted ds by dt, di by dt, and dr by dt, but we have to numerically integrate using that to get predicted S, predicted I, and predicted R, which is why we are calling the solve function with UDE problem as the problem statement. This fifth order Runge-Kutta solver, initial conditions, initial parameter, we are saving at every time point. And then we have an additional parameter here. And then solutions are stored in this variable called solve. Now, I noticed that while running this code, sometimes I was encountering instabilities where the time step was becoming so small and I was facing certain issues. So this block of code I added such that I don't want any not a number kind of parameter in my simulation. So if I get something like not a number, is NaN means is not a number. It's like this, is NaN. If that is what is happening, then I'll return infinity as my solution. And otherwise, where will I return? The value of the loss will be infinity. If any of my numbers is not a number, then I'll say that loss is very high. So I'm penalizing the neural network for making predictions such that you have not a number as one of the numbers. And if that is not the case, then I return sum of absolute value. So abs2 means you are taking this number. This is the predicted solution for SIR. This is the true solution for SIR. You are subtracting that and squaring it, and then you are summing it. And this is basically the mean squared error. And so now you have the loss function. And now we can train the universal differential equation. So in UDE, we'll be training using this function. So this opt function defines the optimization function, the function that we are optimizing for, which is the loss function. And here we define similar to how we define the ODE problem or UDE problem. Here we define the optimization problem that we are going to solve. And so we use the solver, but this time we use instead of Adam. So usually in machine learning problems for optimizing or minimizing the loss, we use Adam as the gradient descent instead of the vanilla gradient descent. Vanilla gradient descent is what I showed you above. But here we are not using Adam also, we are using something called as LBFGS. So it's like a limited memory BFGS. BFGS is like the name of four scientists, four people who came up with the algorithm, if I believe, if I understand it correctly. But basically, it's a long expansion, but it's very different from the way Adam works. I think we can also, we could also implement Adam optimization here, which should also work equally well. But anyways, this is what has worked really well for me. And we can play with different optimizers like stochastic gradient descent, root mean square propagation, or momentum-based gradient descent, or even vanilla gradient descent, or Adam. There are many options here. So here in the train parameters, it is essentially the solution for optimization problem. And then we have the trained neural network. Now it is time for us to make predictions, right? So here the trained solution is the solution for the SIR, which is what is given by the trained universal differential equation, meaning the trained neural network will make a prediction for the ds by dt, di by dt, and dr by dt. And using that, we can solve it, meaning we can numerically integrate it to get the S of t, I of t, and R of t. So here we are solving the UDE problem using the fifth order Runge-Kutta, and then we are passing the train parameters. So if you remember, the only difference is here, instead of these parameters, we were passing P0. P0 was the tau SI and tau IR values, which we defined for the ground truth. This was 0.85 and this was 0.1. But now we are passing the train params.u. So train params.u is the predicted value of tau SI and tau IR, and we are saving at different time points. And then here we are making basically 6 lines. This is the true solution for S, true solution for I, true for R. This is predicted S, predicted I, and predicted R. And one thing to note here is that we are still plotting for the time point 0 to 25 days. So we are not making any forecast yet. Forecast will come only if we are making predictions for days beyond 25, right? So we will do that later in the coding. Once this much is implemented in the code, we can also do that forecasting. So now let us open Julia and let us implement this code and see what we get. So let us go back to the starting of the code. I have opened my Jupyter lab here. So in that, I'll be using the kernel Julia 1.10.9 is the version that I'm using. So first, let me copy all the packages and pasting it here and running it. So here, nothing fancy, or we already discussed this. So I'm not going to go line by line right now because we already discussed the whole code. Then defining the initial conditions and the constants that we are going to be using. So far, no output will be there because we are simply defining the certain parameters. Then the SIR ordinary differential equation. So this function here, we are defining the problem and generating the ground truth solution. So this is the classic SIR model. Then we have the definition of the UDE, the two neural networks that we are using, and the function which basically solves the UDE. So here UDE problem is defined here and we are solving it later. Then we have the loss function, the mean squared error between the predicted value of SIR and the ground truth SIR. Then we have the training. So in the training, we are not using Adam, we are using this LBFGS optimization. And this is the part where we actually we actually train the neural network, right? So this let us run. And in the last part, here we are solving and plotting. So once this is done, we can also do a little bit of extrapolation. We can try to extrapolate from 26th day till 50th day and see what we get. So right now, I hope the code is running. Yeah. So the code is running here. So this is the matrix where the true solutions are there. So 3 by 25 means you have S, I, and R values for 25 days from 0 to 25th day. Then constructing the UDE model. So here, this is the initial number of susceptible population, infected and recovered initial values. Loss function will not return anything. And here, the training, this is the optimizer. So here I have defined only 2 as the maximum number of iterations because I noticed that even with 10 or 15 number of iterations, I'm getting very good results. So initially, to make the execution happen fast, I just defined the maximum number of iterations or epochs as 2. It should hopefully be executed really soon. Yeah, these warnings were happening earlier also when I tried running the code, but I basically ignored the warnings because I was still getting the results, so did not bother to check it. And then in the last part, we are plotting. So let's wait until the code gets executed. Okay, so it is finished and it did not take me too much time. So here the bold lines are the true values, the ground truth. The blue is susceptible, red is infected, and green is recovered. So as we expected, initially the most of the population are susceptible, then all of them get infected, and then all of them recover. So susceptible people go from almost 0.99 to 0. Infected peaks and then it comes to 0 eventually. And recovered, initially 0 people are recovered, then almost everyone is recovered because almost everyone also gets infected if we run the simulation for a very long time. Now what we can do is, let me actually change the number of iterations from 2 to 10, because right now the prediction is not very good, as you can obviously see. So now I'm running for 10 iterations and I just want to see how the results look like. And I hope it will be quite good. Yeah, so this is the result for 10 iterations, much better than what we had for 2 iterations. So number of days, please note it's still 25. So now I'm going to try 20 iterations. Hopefully that will be even better. And If this works really well, then what we can do is we can try to make an extrapolation. So this is the result. It's not significantly different from 10 iterations. Pretty much similar. The dotted lines are the predicted value of SIR. The bold lines are the actual SIR ground truth values. Now what we can do is let us copy this code and sort of do a little bit of an extrapolation. So here I will say extrapolate, or basically forecast, right? That's what we're doing. Forecast to 50 days. So here we need a trained solution, but we want it for more number of days. So what we can do is let us copy some of these parameters and let us paste it here. And then number of days I want to be 50. So this I'll call as number of days 2, 50. Then constants will remain the same. So I don't need this actually. I can delete this because they are not going to change. Time span will be from this to n days 2. Then t equal to, and this I can call as t span 2. T span 2 and length equal to number of days 2. So now the time span will be, this variable, let's say t2 is from 0 to 50. Then I would say trained solution 2 is equal to solve. We are solving the UDE problem and saving at T2, and train parameters remain the same because we are making predictions. And UDE problem, let's see if I need to change the UDE problem. So UDE problem is, I need to change this also. So UDE problem will be, so this I will call as UDE problem 2, and I'm calling the SIR UDE. The initial condition remains the same. T span will be T span 2. P0 vector, that can remain whatever it is. Then here I'll pass UDE problem 2 and save it is fine. And true solution, anyway, it's only available, ground truth is available only till 25 days. So this T I'm not going to change, but this I will keep T2. And I'll use trained solution 2 here. Trained, extrapolated, or I would say forecast. It's not entirely forecast. It's only for forecast after 25th day. Let's see. I hope this runs. Yeah, so now this is running. So here what you can see is we are now plotting from day 0 to day 50. Out of which till 25th day, it's not forecasting. It's literally the training result. But beyond the 25 days, what we are doing is we are forecasting based on the predicted value of tau SI and tau IR. And you can see that the forecast is kind of decent. Basically, you are able to forecast the spread of a virus ahead of time. And you can think of places where this will be very useful. Basically, if you are a government and if you can make accurate forecasts that, this much virus spread can happen unless you do something. If things go just like how it is right now, this can happen. If that kind of forecast is available, it's very good for implementing policies, which is why some of the models like the QSIR model proposed by Dr. Raj, it went so popular during the time of COVID. That paper is so highly cited now. So I'll link that paper. I'll also share this Jupyter notebook with you. And I will also share the Miro board notes. I highly recommend you to try this out. If you don't have Julia, just I'll share one link, which is a video link for how to install Julia and set up all that. Not a difficult thing to do. So with this, I can conclude my lecture here now. So I hope you get a basic idea of how scientific machine learning framework is so helpful in building models that are more powerful than simple mechanistic models or black box ML models. SciML can literally do a really good job by not throwing away the physics from the picture, and also by not relying too much on black box models. So thank you so much for listening. I hope you enjoyed this lecture. See you again in another one. Take care until then. Bye.